This is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So today I want to discuss about thin cylinders. So already in previous sessions I have discussing the solid mechanics and material subjects, various topics already we have discussed. But in this today's session you will learn about thin cylinders. So what are the stresses induced in thin cylinders? So first of all, you should know the introduction to thin cylinders and the outcome of the today's topic. They analyze the stresses developed and deformation of thin and thick cylinders. So first analyze the stresses developed and deformation of thin and thick cylinders due to internal pressure. At the end of the course, the student should be able to calculate and analyze whatever the stresses developed in the cylinders. So the cylinders are two types, one is thin and thick. First we will see the thin cylinders and later we will discuss about thick cylinders. This unit presents the analysis of thin and thick cylinder cells subjected to fluid pressure. So whenever the cylinders are subjected to fluid pressure, so that is internal pressure. So how to analyze the stresses? Example, steam boilers, reservoirs, reactors, nuclear containers, tanks, working chambers of engines, etc. are the common examples. Steam boilers, reservoirs and reactors. So the working chambers of engines, example for this thin cylinder. Our engine cylinder, the cylinder placed inside the engine chamber. So that also considered as a thin cylinder. So in this unit, stresses and strains induced in the walls of the cylinder will be found out based on the geometry of the shell and equilibrium of the forces involved. So first of all, you should know what are the forces acting on this cylinder walls. We will find stresses and then how to derive the equation for the stresses and then how to calculate the strains we will see in this unit. We shall begin by defining a thin cylinder, identifying the assumptions made in the analysis. Some assumptions are made to derive the thin cylinder stresses equation. After finding the stresses, the material of the cylinder strains will be calculated. So first defining a thin cylinder, identifying the assumptions and then finding the stresses and cylinder strains will be calculated. Stresses in wire wound pipes will be considered. We shall then see the limitations for treating a shell to be thin and look for the differences in the behavior of a thick cell as against a thin cell. So the following assumptions are made in order to derive the expressions for the stresses and strains in thin cylinders. The following assumptions, what are the assumptions made? One is the diameter of the cylinder is more than 20 times the thickness of the shell. The shell thickness, 20 times of the shell thickness is equal to the diameter of the cylinder. And then the stresses are uniformly distributed throughout the thickness of the wall. Whatever the stresses developed inside the cylinder, that is uniformly distributed throughout the thickness of the cylinder. Suppose you take is considered as a cylinder. So whatever stresses induced in this cylinder throughout its length is uniform. Next assumptions. The ends of the cylindrical shell are not supported from sides. And then the weight of the cylinder and that of the fluid contained inside are not taken into account. So whatever containing inside the cylinder, suppose any liquid or any gas, that is doesn't matter. So not taken into account. Only we will see the dimensions of the cylinder and internal pressure only. The atmosphere pressure is taken as the reference pressure. So the boundary condition. So boundary condition is here. First of all, we will consider atmosphere pressure is taken as the reference pressure. Now, we'll see stresses. What are the stresses induced in the cylinder? Now consider a thin seamless cylindrical shell of nominal diameter d and shell thickness small t. So which is containing some fluid at an internal pressure of P. So internal pressure not shown here. So that is P. The two ends of the cylinder are closed with walls perpendicular to the shell as shown in figure. So X plane and then Y. So consider this thin seamless cylindrical shell. The diameter is D and the thickness is small t, shell thickness. So we shall consider a vertical plane YY which cuts the cylinder anywhere along the length. So the vertical plane, the Y, it cuts the cylinder at anywhere. Here also you can take and here anywhere you can take. So which cuts the cylinder anywhere along the length. We shall consider the left portion of the cylinder and see the nature and magnitude of the internal stresses acting on the section. So the left portion of the cylinder. So consider left portion of the cylinder, see the nature and magnitude of the internal stresses acting on the section. The stresses will be as shown in figure. So internal pressure, here stress, some stress shown. So later we will discuss about this stress. I will tell you. So this is the resisting stress opposite to this internal pressure. It can be seen that the internal stresses acting over the shaded annular portion of the cylinder, which is the wall area exposed due to the cutting by plane Y. So the direction of these internal stresses will be clearly longitudinal as the exposed areas is in the vertical plane. So thus the stresses will be tensile in nature, so as to maintain equilibrium. The unbalanced force acting on the left wall is called the bursting force, and the force due to internal stresses acting on the wall thickness of the cylinder is called the resting force. The stresses will be tensile in nature. So whatever the unbalanced force acting on the left wall is called the bursting force due to internal stresses acting on the wall thickness of the cylinder. That is called as resting force. So how do you calculate this resting force? We can write the expressions for the bursting resting force. We'll show you here. See, so the internal stresses acting on the wall thickness is called the resting force. The wall thickness, the internal pressure acting, and whatever acting inside the cylinder, inside on the wall thickness, that is resting force. So it can be clearly seen that the bursting force is caused due to the internal pressure acting on the vertical circular wall of the nominal diameter d. Clear? So that the bursting force need to calculate. So resting force is generated by the longitudinal tensile stress acting on the vertical area exposed, the thickness T and diameter D. So resting force you can calculate, and then for equilibrium the resting force should be equal to the bursting force. So what is the bursting force here? The internal pressure is equal to force per area. So the force is here bursting force by area is, that is circular wall, the circular pi by 4 d square. So that the bursting force is equal to P into pi by 4 into d square. So now see the resisting force. The resisting force is sigma L into pi dt. The longitudinal stress acting to oppose this bursting force. So that is resisting force sigma L into pi dt. For equilibrium, these two forces, resisting force should be equal to the bursting force. So resisting force already we calculated, and bursting force also have written equation. For equilibrium, the resisting force should be equal to the bursting force. So now write down the resisting force. This is resisting force, and this one is bursting force. P into pi d square by 4. So sigma L, calculate PD by 4 into T. So this is called longitudinal stress. For equilibrium, the resting force should be equal to the bursting force, and we got internal stress. The stress is longitudinal stress, PD by 40. So indicating the direction in which it is acting and its nature will be tensile. We shall now consider a horizontal diameter plane, that is XS, the horizontal diameter plane, which cuts the cylinder shell in two halves, like this. The stresses have been shown in this figure. See, horizontally, whenever we cut it, the cylinder, which cuts the cylindrical shell into two halves. Now, here shown the stresses, the resting stress is here sigma h, that is called as hoof stress. We shall consider the equilibrium of the top portion of the cylinder. The horizontal pressure acting on the two end walls will balance each other, and hence there will be no longitudinal stress in the wall of the cylinder. In this in cylinder, there is no longitudinal stress, sigma L. So suppose in the wall of the cylinder, previously you have seen a sigma due to internal pressure, sigma L is there. But in this case, the horizontal pressure acting on the two end walls. So the pressure acting on the curved surface of the shell creates the bursting force for this free body diagram, which should be balanced by the reacting force caused by the development of internal stresses along with the wall thickness of the cylinder. Now, the plane XX is horizontal. The cylinder wall exposed by the cutting will also be horizontal, and it will be in the form of two rectangular strips along with the longitudinal direction of length L and thickness T, already shown in this diagram, two rectangular strips. So that the length L, the strip length is L, and the thickness is T. So the stress acting on this strip will be in the vertical direction. So the pressure acting on the curved surface acts normal to the surface, and then it will be acting in different direction at different points along the surface. So I will show you the equation, the radial force acting on the element. So here, see, the radial force acting on the element is, take a small element on this surface. Now you can calculate the radial force, internal pressure into radius into the angle of the small angle of the strip, d theta into L. So the vertical component of the elemental force throughout the cylinder, entire cylinder, what is the vertical component? So the 0 to pi limits and integrate the previous equation, L into sin theta into d theta. So you will get P into d into L. So that the resultant vertical component is acting upwards, the internal stress on the horizontal strip of dimensions L and T will be acting down. So that is nature of the stresses is tensile, and the resting force is sigma h into L into T into 2. 2 times of the thickness into L into sigma. This is stress into area. So that's the resting force. So the equilibrium is maintained by the action of bursting and resting force only. So the resting force is sigma h into L into T into 2, and then the bursting force is PdL. So already we have calculated the vertical component of the element force. This is bursting force. So the pressure acting on the curved surface acts normal to the surface and then act in different direction at different points along the surface. So whenever you integrate it with limits 0 to 5, we will get that bursting force PdL. Now equate these two forces, and finally you get the stress sigma h is equal to Pd by 2t. This stress is called as wave stress. So this stress is called wave stress acting in the circumferential direction, and it will be tensile in nature. Previous one already we calculated longitudinal stress sigma L, and now have derived that wave stress. It can be stated that this states that the internal stresses in a thin cylindrical shell are acting in the longitudinal and circumferential direction. So whatever internal stresses in a thin cylindrical shell are acting in the longitudinal and circumferential directions. Hence, they are named as longitudinal stress and wave stress, and both are tensile in nature. Sigma L and sigma H, these both are tensile in nature. So this stress is called wave stress acting in the circumferential direction, and it will be tensile in nature. So now this at any point in a thin cylindrical shell with an internal pressure P, we have obtained an expression for stresses along longitudinal direction and circumferential direction. Now in this, in order to obtain the strain along any direction, stresses already we have calculated. Now, in order to obtain the strain along any direction, we have to see the state of stress at any point in the 3 mutually perpendicular directions. The stresses are as follows. Stress along the radial direction, that is compressive. Stress along the circumferential direction, Pd by 2t. So already we have derived this is wave stress. Stress along the longitudinal direction, sigma L, Pd by 40. Longitudinal stress, Pd by 40 and Pd by 20. Both are in tensile nature. Now calculate the longitudinal strain. Epsilon L is equal to sigma L by E minus B into sigma N by E. The Poisson's ratio B, mu. So wave strain sigma N by E minus mu into sigma L by E. So now you can substitute the sigma L values and in the sigma L value in this equation. So here epsilon L is equal to sigma L. What is the L? Sigma L is equal to PD by 40 E minus mu into sigma L by L. So the stress along the longitudinal direction, you know. So by using stress equation, you can find longitudinal strain. After simplification, you will get the longitudinal strain. Similarly, wave strain. Here also substitute the above values. We will get the wave strain. So like this, need to analyze the whatever the stresses induced in the thin cylindrical cells and then strains. So these are the references I have taken for this PPT. And is Ramamurtho, Strength of Materials, title of the book is Strength of Material. And then R.K. Bansal, another textbook, a textbook of Strength of Materials. And R.S. Kurmi and Gupta, title of the book is Strength of Material. Publishers are Chand and Co. And the NPTEL Strength of Materials notes I have taken for this PPT as a reference. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.